So welcome everyone to the week 3 review for Math 2413. Like I said, I will be emphasizing epsilon-delta limits in this one because it is a topic that I noticed that a lot of people tend to struggle with. So we'll start with that. And as of right now, if we have a function, we have several different ways to find a limit. We could either graph it out and then just look at it and see, well, where does it go? So that's one method, just estimating using the graph. We can also use the tabular method, where we take values closer and closer to the limit point we're looking for until we get the limit we're looking for. And again, this is more of an estimate than anything else. Another way we can find limits is by simplifying things algebraically. So one good example, I guess, would just be like, well, what's the limit as x approaches 2 of x squared minus 4 over x minus 2? Well, then we can simplify this down to x plus 2 by canceling x minus 2 on top of bottom. And this would be a way to simplify our limit algebraically. Is the screen shaking? That might be because I accidentally moved it a bit. Is it still shaking? It might be because as I write it moves a bit. Okay, I'll try and see if I can keep the shaking to a minimum then. Okay, but these are basically most of the ways we've covered to determine the limit of a function. The problem is, a lot of these are just estimates. Like if we look at the tabular method, we're basically estimating our limit using pretty good numbers, but it's still an estimate. So how do we know it's the actual limit? Same with the graphing method. If we look at a graph, we can look and say we think this is the limit, but we haven't actually proved that it is the limit. So that is where epsilon and delta comes in. The intuition of the formal definition is what I'll start off with. So just why do we have this epsilon and delta specifically? So I'm going to draw the nice big picture of epsilon and delta. Let's say we have a function f of x, and we're looking for the limit at an x value. And we'll call that x value, it's often written c or it's written a. I'm going to be using a right now since that seems most common in 2413. So we always start off with the assumption that we know our limit. So we say, well, I think this is what my limit's going to be. And we point out a specific y value. Well then, if I tell you any range around the y value, I want you to be able to give me a range around the x value so that whenever I tell you this y value range, you should be able to give me an x value range that will give me y values within my y value range. So it's almost like a 3-step game. First, I say, here's a y value. Then you give me an x value that will be closer to my actual y value than the y value that I gave you. Does that make sense? All right. Cool. So if we were to write that down formally, let's see if I can erase all these little blue lines. If we were to write that down formally, what it would look like. Thank you, I guess. If we were to write that down formally, here's how we do it. We call the y value range we're given, we call this epsilon. Oh, gee. Did OneNote just crash on me? Ah, there it goes. Sorry, OneNote is doing weird things. Let me share this one more time. Okay, and y'all can see it again, right? Perfect, perfect. So if we write out our y value range, we call this epsilon. And we call that x value range that we give back, well, this is called delta. So the question we, of course, want to ask is, how close to C does delta have to be to end up within our epsilon range? So where does our x value have to be? How close to A does it have to be to end up over here within our epsilon range? So it's always like an if-then statement. So if our x value is close enough to our A point, then our y value is within our epsilon range. Delta is not quite a variable like A, C, or X. In epsilon and delta limits, what we have is we're always fixing A. A is the same thing as C. You'll see it written like the limit as x approaches A. Sometimes you'll also see the limit as x approaches C. It really depends on who you're going with, which like textbook you're using, or who your professor is. But the point is, in epsilon delta limits, our A value is always fixed. We're always looking at the limit at the same point for a given problem. L is also fixed, and x is like a variable. Well, x is a variable. Delta is a bit different. It's more like saying, I guess technically it can be anything. It's just that we have to pick a delta value based on the epsilon we're given. So if you'll remember, we're always given an epsilon. Sometimes they'll leave epsilon as a variable, but technically it's still like giving it to us. But the point is, when we're given an epsilon, that's when we have to choose a delta. So a lot of delta values will work, but it wouldn't necessarily be fair to call delta a variable. Yeah, it just wouldn't necessarily be fair to call it a variable because it's not like the same as x. Does that kind of make sense? All right, cool, cool. So here is our if-then statement. Whenever we have an x value within our x range, it maps, or it goes to a y value within our epsilon range. Now, this is all still fairly abstract, so maybe let's try and do an example with it, because examples really help solidify things. So our first example is going to be find a delta value such that if we have looking at the wrong problem. All right, so this is going to be the problem. Oops, that should not be an if there. All right, so we're asked to find a delta value such that I should say whenever x minus 1 is less than delta. All right, there we go. Sorry, I was looking at the wrong problem, got a bit mixed up. Question in chat. So L is the limit of f of x evaluated at A. Yes, L is the limit. We always start off by assuming L is the limit, and then we prove that it is the limit by using epsilon delta. So this is, I think, a thing that trips up a lot of students. They're like, well, epsilon delta doesn't actually like find us a limit. Right, it doesn't actually find you the limit. You have to use a different method to essentially estimate the limit. So using graphing method, a tabular method, or algebraic simplification in order to get the limit, then once you have the limit, you can use epsilon-delta limit rules to prove that it is the real limit and not necessarily just an estimate you make. Does that make sense? Yep. Okay. So our example is to find a delta such that whenever the absolute value of x minus 1 is smaller than delta, then the absolute value of 2x plus 3 minus 5 is smaller than 0.1. So if we were to write our limit statement out for this problem, oh, come on. What is OneNote doing? Okay. All right, there we go. Sorry about that. So if we were to write out our actual limit statement, limit as x approaches a of f of x is equal to L, well, it's basically just matching things up. We always know that in our delta statement, we have x minus a. So a should be equal to positive 1, because when we're subtracting a, we would need to flip the sign. So we would have the limit as x approaches positive 1 of, in this case, f of x always goes right here. It's always f of x minus L. So we would have f of x is 2x plus 3 equals to 5. So this is the limit statement. This is the corresponding epsilon delta inequalities that we would need to write. Now let's actually work on finding a delta. Now the big idea here is I want to find some way to substitute this in to here. That's how basically every epsilon delta proof is going to go. So let's see what I can do. I'm going to start out saying 2x plus 3 minus 5 is smaller than 0.1. And then I'm just going to simplify this left hand. I can combine my plus 3 and minus 5, and that gives me 2x minus 2 is smaller than 0.1. Now if I factor 2 out, I get 2 absolute value of x minus 1 is smaller than 0.1. Now if I divide both sides by 2, I have the absolute value of x minus 1 is smaller than 0.05. Well, I also know that the absolute value of x minus 1 is smaller than delta. Well, since these are the same thing, and I get to choose a delta, delta isn't necessarily fixed, I get to choose it, I'm going to say that delta is equal to 0.05. And this would be my answer. Now, one way I can check that it's my answer is I can work backwards. I can start by saying x minus 1 is smaller than 0.05, because whenever x minus 1 is smaller than 0.05, this equation, my corresponding 2x plus 3 minus 5, should be smaller than 0.1. So if I multiply both sides by 2, that would be 2 times the absolute value of x minus 1 is smaller than 0.1. So the absolute value of 2x minus 2 is smaller than 0.1. So then 2x plus 3 minus 5 is smaller than 0.1. And I know that I found a good delta of 0.05. Question?
Yeah, so the x minus 1 less than 0.5. So is that when this is what you would do when it says like proof delta is epsilon or
Sorry, I'm
like
having a bit of trouble hearing you. Could you maybe speak up?
yeah, is this better?
Maybe a bit. Let me see if I can find a volume control anywhere. Let's see. All right, try now.
Hello?
Yeah, that's better. Thank you.
Okay. So on the right side you did x minus 1 is less than 0.5, x minus 1 in the absolute. So is this where it basically says like proof epsilon and delta are equal or something along the lines like that?
Um, I don't think I've ever seen like prove epsilon and delta are equal. It is sometimes true that epsilon and delta can be equal, but that would be like a specific case. And there's not really any point to saying that they would be equal other than just saying that you could find a delta so that whenever you have your x minus a is less than delta, then you have your epsilon statement being true. But I can't say I've really ever seen someone ask like prove that epsilon is equal to delta.
Oh, okay. So the left side where you found the 0.05, so when let's say we have a question like find a delta such that like this question, would we also have to show this proof that it going backwards?
Not necessarily. It might depend on your professor. It would never hurt to show it, especially
Okay.
because when we did show this, we knew that our delta was correct, right? We started with this, and then we showed because x minus 1 was less than delta, then this statement was true. So it's not like it hurts. Sometimes it will be harder than this. If you do find a delta, though, and you show your reasoning, it's not like they can really dock you. But I would recommend trying to show that it's correct as well.
Okay, thank you.
Any questions on this example? Yeah, go ahead. You did have a question, right? I'm just assuming you were typing it out in chat, so I'll wait a minute or so just to make sure. All right, I think I'm okay. Cool. After the arrow, how did you get from the third line to the fourth line down when I added the -5 and the +3? Okay, good question. So really, I kind of cheated a bit because, well, it's not like cheating. It's mostly just using parts from earlier to tell me what kind of hints I should use. So you'll notice that my first step, I'm kind of jumping around a bit. My first step working forwards was to combine my -3 and my +5, or my +3 and -5, sorry. Well, I know that on this right-hand side, I'm trying to work backwards. So to get from here to here, I combine the +3 and -5. To get from 2x minus 2, it's almost like I uncombine them, so I split -2 into +3 and -5. Make sense? So it's almost like I just use the hint when working forward to know what I should do when I'm working backward. Right, I don't actually add it to the other side because it's the same thing as -2. It's like saying if I wrote 2 is equal to x, well, if I split the 2 up into 1 plus 1, well, then I wouldn't add 1 to either side because 1 plus 1 is just the same thing as 2. So you could see if I actually went ahead and simplified this side, well, my 2x stays the same, but then I just combine my +3 and -5 and I get -2, which is exactly the same thing. So it's just the same thing, just written a different way. Yeah, no worries, good question. All right, in that case, we'll go ahead and move on to a practice problem. So you guys try this out on your own. I'll give you a few minutes to work through it, and once we're done, I'll go over it with you, kind of like I did with this example. So here we go. Again, it's going to be find a delta bigger than 0, such that that's what the ST stands for, such that whenever, oh my goodness, my spelling is terrible today, x minus 3 is smaller than delta, then the absolute value of 3x minus 1 minus 8 is smaller than 0.05. All right, good luck. If you do get an answer, you can feel free to put it in the chat. In fact, that would be fun. We could do it if you're comfortable, of course. If you're uncomfortable sharing your answer. All right, cool, cool. We've got 1 delta equals 1 over 60. Anyone agree? Anyone disagree? You got 0.0167. Okay. I believe that's actually the same as 1 over 60. So one person agrees. Does anyone need a bit more time to work it? Need some more time? All right. That's all right. We'll keep waiting a few more minutes so everyone has a chance to work it out. All right, you done? Did you get the same answer or something else? All right. Cool, cool. Well, let's take a look. 0.05 over 3 is actually also the same as 1 over 60. So let's go ahead and take a look. Here we go. All right, another, you might be off by 1 if you got 0.167. I believe the correct answer should be 1 over 60, which is 0.0167. So let's take a look at why we get 1 over 60 as our answer. So again, we need to start by trying to substitute x minus 3 is less than delta into here whenever we can. But I notice right off the bat that I can simplify 3x minus 1 minus 8 because I can always combine my minus 1 and minus 8. I get 3x minus 9 is smaller than 0.05. Then I take out my 3, and then I can divide both sides by 3. This is, I think, where some of the ambiguity is coming in, why some of you guys are getting the same answer but in different forms. 0.05 over 3 is the same as 1 over 60, which is also the same as 0.0167. So then we also know that x minus 3 has to be smaller than delta, since we have x minus 3 on each side, right here and right here. We get to choose delta, we can just say delta is equal to, I prefer the fraction form, 1 over 60. So there's our delta. Now let's also go ahead and verify it since we're already here. So we start with x minus 3 is smaller than 1 over 60. Now remember, I want to work backwards. So the first thing I did, or I guess the last thing I did to find my delta was divide by 3. So the first thing I'll do is multiply both sides by 3 because I'm working backwards. 1 over 60 times 3 is 1 over 20. This is also equal to 0.05. I pulled my 3 out of my absolute value, so now I'm going to distribute it back in. And the first thing I did, the last thing I'll do when working backwards, is combined my -1 and -8, so now I'll split those apart. That would give me 3x minus 1 minus 8 is smaller than 0.05. So because we started out with x minus 3 is smaller than delta, and we got 3x minus 1 minus 8 is smaller than epsilon, we know that we have the right limit. All right. Now, can any of you guys write the limit statement? So the limit as x approaches what value of what function is equal to what limit? I guess we'll start with what is the a value? A is equal to 3. Good, good. What about the function? And you're saying 3x minus 1. All right. And finally, what is the limit? 8. Perfect, perfect. Yep, all good answers. And of course, if we wanted to double check that we did have the right limit, we could easily just plug in 3 into 3x minus 1. 3 times 3 minus 1 is, of course, 8. But then we went ahead and proved this limit. All right. Yep, go ahead. Question?
So I do it like a different way. I figured out why my answer was wrong. It's because I put epsilon as I put it as 0.5 instead of 0.05.
Right,
But
right, yeah.
I
That
put
would,
like, yeah, I use 3x minus 1, and then I just add the 0.05 to 8 and subtract 0.05 from 8, and then I just solve for x.
So the main issue with doing it that way is we actually have these absolute value bars here, right? Oops. Those are right there. So when we have these absolute value bars, we can't necessarily just subtract 0.05 from each side. Because they will do weird things to your inequality and also to whether or not you can even add and subtract things. I guess one quick example we could do is what if we had like absolute value of x minus 1 is equal to or even just like 2. Well, if we wanted to subtract 2 from each side, we could have absolute value of x minus 3 is equal to 0, but these aren't the same thing. Let's see, because when we solve absolute value equations, remember we have to split it up into the positive x minus 1 is equal to positive 2, as well as the negative side. X minus 1 is equal to negative 2. When we add and subtract, well, here we have a 0, so now x minus 3 is equal to positive 0 or negative 0. That's the same thing. But you can see here we have 2 equations. Here we only have 1. This only gives us 1 x value. This one, though, gives us 2. So can you see how these would be different and maybe cause problems?
Yeah, but when I was trying to say it, like, because so like for the one that we just did, you know how in the absolute value when we put the function minus the limit,
Right.
I put it like because I know that the function is 3x minus 1 equals 8, which would be the limit, right? But
Right.
instead, because you know how when you do the graph, you have to go up well, in this case, you would go up 0.05.
Yeah,
I
so
just
you're
solve for
saying like,
x exactly without the absolute value. So I solved two different equations,
okay, so you're saying
if
you
that makes
solved like
sense.
3x minus 1 is equal to like 8.05, and also 3x minus
Yeah,
1 is equal to 7.95.
yeah,
Okay, I mean, technically this way works, but I will say only in like, it tends to make things more difficult. For instance, what if your function gives you a bigger delta on one side? So if here's your a value, what if you only have valid deltas for like this far on one side, but a much larger range on this side? Then, well, you'd have to pick the smaller one. Or also, this is actually the next question I was going to go with. What if, instead of having a 0.05 here, I just wanted you to find it for a general epsilon? So instead of giving you epsilon, I want you to find me a delta for any epsilon that I give you. Well, then it's a bit more tricky, right? If you were to set it up with this, you would say like 3x minus 1 is equal to 8 plus epsilon, and 3x minus 1 is equal to 8 minus epsilon, and all of a sudden you have 2 variables.
yeah. Okay,
Yeah,
that
so
makes sense.
that's when it could get a bit more difficult, if that makes sense. Your reasoning is sound, but it's just like it'll make things more difficult for you. But good thinking. Yeah. But do you understand like the other way of using by using epsilon and delta rather than solving just for x?
Kinda. Because the reason I was doing it that way is because it makes more sense to me. But now, like that you said, like if epsilon wasn't given to me, then yeah, I would have to use the other way.
Yeah, yeah. All
Yeah,
right.
it
Can anyone
kind of makes
solve
sense
it?
now.
Yeah, yeah. That's good. Just try a few practice problems. You'll get there. Can anyone solve it using just an epsilon instead of 0.05? saying delta is equal to epsilon over 3. All right, cool, cool. I would actually agree with that. The easiest way to see that is instead of putting 0.5, we can just put epsilon wherever we see it. So instead of having 0.05 over 3, it would be epsilon over 3 instead. Our delta would be in terms of epsilon. Again, we could verify it. This would be less than epsilon over 3. So then 3 times each side would be less than epsilon. And again, it would all be less than epsilon in the end. So yeah, that would be if they didn't give you a specific epsilon, you would have to find delta in terms of epsilon. And you could say that delta is equal to epsilon over 3. If you get a question asking for the largest valid delta, should we split the equation into 2? I would say, in general, it's probably not great to split your equation into 2. Let's see. If you get a question asking about the largest valid delta, for any linear function, the largest valid delta is the same on each side. For any nonlinear function, it's really hard to find the largest delta for any epsilon, so they usually won't ask for a nonlinear function. Let's see. So for a linear function, your largest delta will be the same regardless of which side you're looking at. And I was actually going to do a nonlinear one next. And the way you are supposed to solve it basically doesn't always give you your largest possible delta. It just gives you a delta that will work for any epsilon. So I would say in general, if you have a question asking for the largest valid delta, if it's a linear function, you really don't need to worry that much about it. You just need to follow the same process we did here. And if it's a nonlinear function asking for the largest valid delta, I would reread the question, because you're probably reading it wrong. Does that answer your question? When do you need to split the equation into 2? Okay. Your instructor did this during class. Do you have the function he was doing it with? Was it a linear function or a non-linear function? And if you don't know, that's all right. Let's see. You think it was an x cubed equation. Okay. All right. So let's actually take a look at a nonlinear function. We won't do x cubed. X cubed is it would be fine, but I don't want to do x cubed. OneNote is bugging out on me again, so hopefully it'll be all right. Okay, there we go. And you guys can see the screen again. Perfect. Okay, so let's do a nonlinear example just to see what it would look like when we maybe have to split the function. Let's see. There we go. Find a delta greater than 0 such that whenever the absolute value of x minus 4 is smaller than delta, then the square root of x minus 2 is smaller than 0.1. So we'll start with a given epsilon and see if we can work our way through from here. Okay. Well, this one is going to be a bit weird because we do have a square root in here. So let's first write our limit statement. We have x minus a. In this case, a was 4, so limit as x approaches 4. F of x is square root x, and L is equal to 2. Is that a negative square root of x? No, that is just how I write my square roots. I can maybe clarify it a bit. Here we go, like that. I don't know if that helps at all. If I write a negative, it'll be definitely different. I would tend to write it more like this, so that there's a clear gap. Not a negative square root. Sorry about my handwriting. Okay. So in this case, I'm actually going to start with my absolute value of x minus 4 is smaller than delta equation. Why? Because, well, I'm actually going to do a bit of sneaky difference of squares. So everyone remembers difference of squares. Like if you have x squared minus a squared, you can factor that into x plus a and x minus a, right? Well, secretly, x just by itself is also a square, right? It's the square root of x times the square root of x. So x minus a squared then would be the square root of x plus a times the square root of x minus a, right? It's a bit weird to think about, but this is actually how I'm going to factor my x minus 4 is less than delta. I'm going to say this means that the square root of 2, not the square root of 2, the square root of x minus 2 times the square root of x plus 2 is then smaller than delta. So just rewriting x minus 4 by factoring it in a kind of weird way. Now, one of the properties of absolute value is that I can actually split up multiplication within it. So I'm breaking apart my absolute value because this is also the same thing, right? One way you can think about it is up here we've got the absolute value of the whole side, so it should be positive. And here we also have the absolute value of two things, which are then multiplied together. So it should be a positive times a positive, which should also give us a positive out. All right, so now I have this. Now I'm looking for an x minus 2 by itself, or a root x minus 2. So I'm going to divide both sides by the absolute value of the square root of x plus 2. Right? So that tells me, why do I keep writing square root of 2? The square root of x minus 2 should be smaller than delta over the absolute value of the square root of x plus 2. Well, this is actually where a bit of tricky stuff comes in. I know that the absolute value of the square root of x plus 2, well, square root of x is always bigger than or equal to 0. So then the square root of x plus 2 is always bigger than or equal to 2, right? So then the absolute value of that is also bigger than or equal to 2. Well, if I'm dividing something by more than 1, it's going to get smaller. So I can actually say that delta divided by a number bigger than 1 is going to make delta smaller. So I can say that delta divided by the absolute value of square root of x plus 2 is in turn smaller than delta itself. Does that make sense? Could I repeat that? Sure. So basically the idea behind what I'm doing here is I'm saying delta divided by 2 is always going to be less than delta, because I know that delta is bigger than 0. Well, in this case, instead of having a 2 right here, I have the absolute value of the square root of x plus 2. But what I'm saying is that the absolute value of the square root of x plus 2 is always bigger than or equal to 2, because I know that the square root of x is always bigger than 0. So the square root of x is bigger than 0. So then the square root of x plus 2 is bigger than 2. So then when I take the absolute value of both sides, we get the same inequality. So because I'm dividing by something larger than 1, if we were dividing by like 1/2, that would be like multiplying by 2. But because we're dividing by something larger than 1, it should make our total fraction smaller than the original numerator. So I'm just saying that delta divided by the absolute value of square root of x plus 2 has to be smaller than delta. Does that make sense? All right, cool. Oh, oops, what in the world? Here we go. Oh dear. Okay. Why are there 3 less than signs? Like, why do I have one thing here, and one thing here? The reason is this is kind of an intermediate step. This is something awkward. I don't want to have to deal with delta with an epsilon in terms of x. That's going to make things too painful, too hard. So what I'm saying is I'm using this as an intermediate step to say because this is less than this, and because this is less than this, I can then write x minus 2 is smaller than delta. Does that make sense? Yep. Well then, now I can actually pull down my original epsilon. So because the square root of x minus 2 is smaller than delta and smaller than 0.1, I can choose my delta equal to be 0.1. Or in other words, if we had a general epsilon, we could let delta just equal epsilon. Since 0.1 we could also replace with like an epsilon. But this would be the delta for the given epsilon. Does that whole process make sense? When I multiply x to the 1/2 minus 2 by its conjugate, I thought you were supposed to multiply by the denominator by the conjugate as well. Okay, so the thing is, I'm not actually multiplying by the conjugate here. I can see how you would get confused. In general, yes, except in this problem, I decided to start with the delta equation because I noticed that if I factored it using my difference of squares, if you look over here, using my difference of squares, well, then it would get me at least half of my epsilon equation, half of what I'm looking for. I was looking for x minus 2, the square root of x minus 2, so I tried to get this portion of my factored part. So it's not multiplying by the conjugate, I really just factored x minus 4 into the square root of x plus 2 and the square root of x minus 2. Does that make sense? Yeah, don't worry about it. All right. So we found our delta based on our epsilon. Question? Go ahead.
Yeah, I don't know, you might have already repeated this, but how did you get the 0.1 for s? Like the absolute value square root x minus 2 less than delta? Like,
Where did I get like the 0.1? That is just given in the problem. It's what I originally decided epsilon to be, just for the purposes of the problem. So usually they'll either give you an epsilon or they'll tell you to find delta in terms of a general epsilon. The 0.1 was just the given epsilon they wanted you to find a delta for.
Okay. So how did you go from the one above it, the equation, to the one below it?
So how did I get, sorry, could you repeat that?
How'd you get absolute value square root x minus 2 less than delta over absolute value square root x plus 2 less than delta to absolute value square root x minus 2 less than delta?
Okay, yeah, that's a good question. Do you understand how I got this equation?
Yeah, you just kind
Right,
of
right.
graphically used different squares and then just kind of moved around absolute value.
Right. So this is actually a property called transitivity. And it says, well, if one thing is less than another, and that other thing is less than a third thing, well, because A is smaller than B, it should also be smaller than C. An easy example is like, well, I know 1 is less than 2, and 2 is less than 3, so then 1 has to be smaller than 3. It's like saying, because this is the biggest, bigger than this, well, then it should also be bigger than this. Make sense?
Oh, okay, so you just cut out the middle part.
Yeah, I just cut out the middle bit. All right.
Okay, that makes sense.
Mm-hmm. Could I re-explain how I got delta over 2? So this equation right here, I basically just created as an example to explain this more complicated one. Basically to say why delta over the square root of x plus 2 was smaller than delta itself. So this actually doesn't really have any relation to the problem we have. The reason delta over the square root of x plus 2 is smaller than delta is because this is bigger than 2, so dividing by something bigger than 2 is going to make your original number smaller. Right. Delta divided by a number greater than 1 is actually smaller than delta. Point 1, would that be wrong? Okay, thank you. Yep. Let's see, if you're, well, the thing is, it's like, if we put an x in our delta equation, then suddenly we have, if they didn't give us a specific epsilon, suddenly we're using delta, we're using x, and we're using epsilon all at once. In general, we want to avoid that because that's hard. It might also be wrong. I've certainly never had to use an x in my delta equation. So try to simplify it so that delta is in terms of just epsilon and not x. If you have an x in your delta equation, you probably are doing something wrong, or you can simplify somewhere to make it easier. And we cut out the middle part, not because absolute value is a range, but because we don't want to deal with the middle part. We don't want to deal with having an absolute value of square root x plus 2 in our delta equation. So we can say that because it's smaller than delta, this inequality holds. So we just cut it out because it's too difficult to deal with, and we found an easier way to deal with it. Like, would you rather have your epsilon in terms of delta over square root x plus 2, or just in terms of delta? Well, I'd rather have it just in terms of delta because that's a lot easier. Yeah, of course. This is like writing inequalities to simplify things is usually one of the ways you can deal with more complicated epsilon delta problems. When you're just dealing with linear equations, it's usually pretty easy because you should always be able to make a direct substitution, like we did in earlier problems. When you have like square roots or squareds, then it might get a little more difficult. I do notice that we actually didn't end up splitting our equation in this one. I can show an equation where we do have to split, but I don't necessarily want to do that quite yet because I do want to touch on continuity. So if we have time at the end, I'll go ahead and show one of those. Sound good? Cool, cool. All right. let's talk about some continuity then. All right. Cool. So let's say we have a function f of x, and we say that f is continuous at a if three things are true. One, we have to be able to say what f of x is. So f of a is defined. If I ask you what f of a is and you can't tell me, it's not going to be continuous. We have to have a defined function there. Second, our limit also has to exist. If our limit does not exist, then we also have a problem as well. Finally, if both of those things exist, well, the limit has a function value. So let's go over three different possibilities, or a few different situations in which maybe these things aren't true versus when maybe they are. I'll go ahead and draw a coordinate plane. And let's say we have a function like this. Just a function with a hole in it. Well, we know that functions with holes in it shouldn't be continuous, right? So if this is a, well, f of a doesn't have any function value associated with it, right? So it actually does not exist. So because it doesn't exist, then we say that f is not continuous because it doesn't exist at that point. But what if it did exist? It was just at a different spot. Well, if this is 2, we can say, look, our function exists. It's 2. Cool. We can even say, if this is 1, just looking at the graph, as x approaches a, well, we can clearly see the point it's going to if we just trace along it. I'm going to do it really gently like this. If you trace along it, you can see the point we're approaching is, of course, this hole right here. So the limit would be just 1. So in this case, we can see it's discontinuous because of our third property. The limit as x approaches a of f of x is equal to 1, and that is not the same as 2. So in this case, it would be discontinuous because it violates the third property. Now, what if we had a function that looked slightly different? Oh, that's actually what I wanted to erase. What if it looked like this instead? Well, clearly we still have f of a as defined. That's still 2. The limit as x approaches a, though, well, if we approach from the left, we're approaching the point positive 1. And if we approach from the right, we're approaching the point positive 2. So since the limit from the left does not equal the limit from the right, we say our limit does not exist. So then it would violate the second property, and that's why it's discontinuous in this case. Any questions about continuity? Or about this definition of continuity? Yeah, go ahead.
So this was a problem in our like web assigned just like on our textbook homework. I kind of like watched some random YouTube videos on like Sunday night and I figured it out. It's about continuity. I still kind of don't understand it. I was going to review it because I have a quiz tomorrow, and
Okay.
I was looking at it in the morning and I didn't understand it. Could we do a problem like that?
Sure. Can you describe it for me?
Yeah, so the question is find the values of A and B that make f continuous everywhere. And
Okay.
it's f of x equals, there's three equations. So
Right.
x squared minus 4 over x minus 2. And that's if x is less than 2.
Right.
And the
I'll
second
just use a
equation,
similar problem because I don't want to give out like homework answers.
right.
But I get what you're saying. I do know the type of problem, so we'll go ahead and do that kind of problem as an example. Let's say we have three sets of equations. We'll go with 2x squared minus a if x is less than or equal to 2. We'll go with its b plus x as x is equal to 2. And lastly, we'll go with, I don't know, 3a minus 1 when x is bigger than or equal to 2. Sound good?
I feel like this one, like I can do this, but I can't do, can I just read out the full problem? You can see if it's like similar or not.
Yeah, sure, go for it.
Okay, so we have like the x squared minus 4 over x minus 2 if x is less than 2. And then the second equation is ax squared minus bx plus 3 if 2 is less than or equal to x, or x is less than 3. And then the third equation is 4x minus a plus b if x is greater than or equal to 3.
If x is, sorry?
Greater than or equal to 3.
So this one would be, not x is smaller than 3. I'm not going to bother writing that out super nicely. Okay.
Yeah, so the second one yeah, that's basically the same thing, so they just kind of combined it.
Right. Okay. Let's see if we can come up with a problem that is somewhat similar, but not just the homework. Let's see, here we have 2 is less than x is less than, we'll go with 4. And here we'll make it ax squared plus 3x minus b. And this one will go a plus 4x. I don't have 4x, a plus just bx. And this would be for x is bigger than or equal to 4. Okay, hopefully I made a system that would actually be solvable, but we'll never know until we start. So in general, the biggest thing to remember for these problems is the limit from the left has to equal the limit from the right. So for every point where you could possibly have a discontinuity, and in this case it's usually at the points where you switch your piecewise, so 2 and 4 in this case, you want to check to make sure your functions are good. So my first question is, what is the limit as x approaches 2 from the negative side of your function? And you're saying 8 minus a. All right, I would agree, because if we're approaching from the left side, we need to use our first equation, the one where x is smaller than 2. In this case, it would be 2 times 2 squared minus a. This, of course, is 8 minus a. Okay, what about the limit as x approaches 2 from the right side? You say the same. I would not say it's the same. Let's see, someone else is saying 4a plus 6 minus b. I would actually agree with 4a plus 6 minus b. Yep, don't worry about it. So since we're approaching from the right, where x is greater than 2, we want to use the function where x is greater than 2. And we want to use it near the point where x is equal to 2, so that's why we wouldn't use the last one. We would use ax squared plus 3x minus b, and that would give us 4a plus 6 minus b. Okay, well, in order to be continuous, we know that our limit has to exist, right? And in order for the limit to exist, the limit from the left has to equal the limit from the right. Or in other words, the limit as x approaches 2 from the negative side should equal the limit as x approaches 2 from the positive side. So because we found the limits, we could say that 8 minus a is equal to 4a plus 6 minus b. Make sense? All right. Well, just knowing this isn't necessarily enough to solve for a and b, right? We have one equation but two variables. So we need to maybe come up with another equation. How could we come up with another equation? We say combine like terms, and we also say find the limit of as x goes to 4. So I would actually agree with find the limit as x goes to 4. If we combine like terms, it makes things cleaner, but it's still going to be the same equation. So I will go ahead and combine like terms just to make things cleaner. I'm going to put all my a's and b's on one side and everything else on the other. So I get 2 is equal to 5a minus b. But what we actually want to do is we do want to find the limit as x goes to 4, because that will give us a whole nother equation. So what's the limit as x goes to 4 from the negative side? (16a plus 12 minus b). Perfect, perfect. And what about from the right-hand side? All right, so we're doing the limit as x approaches 4 so that we can get a second equation. We can't solve one equation with two variables in it with just the one equation. We need another equation in there so that we can solve it. We would get as our other limit a plus 4b. Hopefully, if we keep working it a little further, maybe you can see. All right, cool. Makes sense? Perfect, perfect. So then, because the limit is approaching the same point, the limit from the left should equal the limit from the right in order for a limit to exist and it to be continuous. So then you could say 16a plus 12 minus b is equal to a plus 4b. And again, if we put everything like terms together, we would have 12 is equal to minus 15a plus 5b. Okay, well now we have two separate equations, one right here and one right here. So I'm going to write them as a system of two equations. Okay, so now we have two equations and we can solve these for a and b. There are a lot of different ways you could solve it. You could do it by substitution. You could do it by elimination. Just however ways you've learned to solve systems with two equations in, I guess, algebra. I'm going to solve it by elimination just because I like elimination. So if I multiply this equation by 3, then I have 12 equals to minus 15a plus 5b, and my second equation would be 6 is equal to 15a minus 3b, and then I just add my equations. 18, I have minus 15a plus 15a is 0, so 18 is equal to 5b minus 3b is 2b, so b is equal to 9. Now, because I have a b value, I can substitute my b value into either one of my equations. I'm going to choose 2 equals to 5a minus b because that one's easier. So then I get that 11 is equal to 5a, and a is therefore 11 over 5. Make sense? Cool, cool. All right. Everyone good on how to solve these kinds of problems? You just want to make sure your function is satisfying all three properties of continuity. So you have to make sure that the limit as x approaches every point exists. You have to make sure that every point or every intersection point actually has a value, an x value, a y value, sorry. And you also have to make sure that your limit is equal to your function value. Oh, cool. So you're good to go. Yeah, the wording is definitely more confusing than the process. But in general, just try and make the left side equal the right side. Easiest way to think about it for me, at least. Okay. Let's see. That is really all there is to continuity. There's not a whole lot to talk about. We are getting short on time, so we can either do a practice problem with continuity or another more difficult Epsilon-Delta problem. Which one would you prefer? Quadratic? Okay, difficult Epsilon-Delta. All right. Oh boy. Okay, so yeah, this one we can talk about some fun concepts. So let's say your function f of x is equal to x squared. We're just going to keep it fairly straightforward because I mostly just want to illustrate some concepts with it. So it's quadratic, but all the complexity is just from the quadratic bit. We're not going to work on adding constants or anything. And we're interested in the limit as x approaches 2. Why not? Okay, so as x approaches 2. Well, we can know just by plugging in 2. The limit as x goes to 2 of x squared is equal to 4. So if I were to write my epsilon delta, or if I were to write my two inequalities, first one would be x minus 2 has to be smaller than delta. And my second one would be f of x, which is x squared, minus L, which is 4, is smaller than epsilon. And I have to find a delta for any epsilon so that whenever x minus 2 is smaller than delta, then x squared minus 4 is smaller than epsilon. Okay. Well, this might be a bit tricky. All right. How did I do this? So I'm going to start by saying if we multiply, let's start with our x minus 2 is smaller than delta. If we multiply both sides by x plus 2, the conjugate, well then what we get is the absolute value of x squared minus 4 is smaller than the absolute value of x plus 2 times delta. Okay, well that's all cool, but we don't necessarily want an epsilon in terms of x. So this side is still a bit of a problem. Yep, let's hear the question.
Yeah, I have a question. When do we use, like, in the beginning we started using the right absolute value equation, and now we're using the left side. When do we use which side?
It is entirely up to you. For me, I'm basically going based on which side I think is going to be easier to turn into the other side. So I could have factored the right-hand side into x plus 2 and x minus 2 and had that be smaller than epsilon. But then it's like I still am left with the same problem of oh, I've got an x plus 2. For me, it's like whenever I'm thinking it might be more complicated, I'll start with the left-hand side with my delta equation, because it tends to give me a little more flexibility with what I can do to delta. For linear ones, I like to start with the epsilon side, just because linear ones tend to be pretty straightforward. You just factor like a constant out usually and divide both sides over. It's really up to you, though. It doesn't make a difference as long as you're careful with your signs and making sure you're not getting any wrong inequalities. But you should end up with the same answer either way. I know it's
Okay.
probably not the answer you were looking for, but it's basically whichever side I think will be easier I start with.
Okay, thank you.
Mm-hmm. All right. Okay, so let's see. Where were we? Okay, right. We were complaining about how the absolute value of x plus 2 times delta is hard to deal with. Yeah, we don't necessarily want to deal with that. So in this case, here's what we're going to do. We're actually going to split it up. I'm going to say, I know that the absolute value of x plus 2 times delta is going to be smaller than delta if and only if the absolute value of x plus 2 is smaller than 1. Right? Because if I'm multiplying by something smaller than 1, it's going to get smaller. So when does this happen? When is the absolute value of x plus 2 smaller than 1? Well, then I can say that x plus 2 is bigger than -1 and smaller than +1. So then, if I want to turn it back into x minus 2, because I know how x minus 2 compares to delta, I could subtract 4 from all bits of this. So -3, oh no, -5, sorry, is smaller than x minus 2 is less than -3. I think I'm going in the right direction with this. It might take me a minute to remember, though. Hmm. Why did I subtract 4? I subtracted 4 because I'm looking for specifically an x minus 2, because that matches what I have here. So if I took the absolute value of each of these, I would have 3 is less than the absolute value of x minus 2 is less than 5. Right? Yep. So, where was I going with this? I think I maybe took this the wrong direction. So we try to make, yeah, you pretty much always try to make the delta equation equal to the epsilon one, because then you can say something about how epsilon and delta are related. If you don't have equal equations, you can't really compare your epsilon and your delta. And that's the whole point of doing epsilon-delta limits. Yep. So give me one moment. I'm going to try and think this one through. Let's see. I'm just going to write a bunch of stuff down. I'll see if I can explain it in a bit. So Okay, right. I think this is actually what I'm going to go with. Okay, so yeah, this is what we're going to go with. So if we look all the way back at our original picture for our epsilon delta limits, think way back, way up here. Let's see. We'll scroll all the way up. Okay. Looking back at our original picture, then we have a couple of options for what to do with our delta. So all we have to do is pick a delta that'll fall within our epsilon range. So let's say we pick this delta range right here. Oh, that's not the right range. Our 8 point is right here, so our range would be about like right here to right here. Well, then that'll trace all the way up to an itty bitty epsilon range up here. But since we start out with an epsilon range, if we make this epsilon range really huge, like let's say here to here, well, this same delta range still works, right? It still gives us a little bitty epsilon range in there. So if we pick like a fixed delta, like delta is equal to 1, well, then it'll work for any really big epsilon. So if we pick a smaller delta that'll work for any big epsilon, then we can kind of ignore any big epsilon. So that's kind of the principle behind what we do when we split it up. Here we go. We go back down to our problem. Here's what I'm going to say. I'm going to say delta is going to be the minimum of 1 and some other number. Because I don't want to have to think about big epsilons. I want to only focus on when x minus 2 is smaller than delta. So that automatically tells me that because delta is at most 1, because I'm picking the minimum of 1 and something else, delta x minus 2 has to be smaller than 1. Does this kind of make sense? How do I know that delta is at most 1? The thing is, I'm basically choosing delta to be at most 1. Because part of our epsilon delta limit is that we can choose delta, and as long as it works for the epsilon we're given, it's okay. So the thing is, I'm splitting up my problem to consider the very big epsilon ranges, so the ones like right here, where they give me points really not very close to my actual limit at all. I'm saying the same little delta value right here is going to give me a good range that'll work anyway. I don't have to find a tight delta, I just have to find a delta. So I'm saying this little delta is going to work if they give me a really big epsilon. So then I'm saying, if I can just ignore the really big epsilon, I can focus on the small ones. We don't know epsilon, so after we basically say, I don't want to focus on all the big epsilons, I can use the same delta for all the big ones. Now we need to say what happens with the small ones. Does that make sense? What do we do for the small epsilons that are delta that we picked that delta equals 1 won't work for? So you're right that we don't know epsilon. I'm saying if we pick, we're almost splitting up the problem to say, well, what do we do for epsilons from here to here? In this case, I'm going to say delta is equal to 1. But what if we have epsilons from here to here? Then I'm going to say delta is equal to something else. Does that kind of make sense? Why do we always, well, we don't necessarily assume that epsilon is big. We say, we're saying that epsilon could be anything, but if epsilon is big, I know how to handle it. So it's more like, let's see, how do I describe this? So the idea is when someone gives us an epsilon, it's almost like we're making a choice. If they give us a big epsilon, we can go to the delta that we picked of delta equals to 1. If they give us a little epsilon, well, that's why we're taking the minimum of 1 and something else. This is almost like making a choice. We can say, if you gave us a big epsilon, I'm going to make delta equal to 1. If you gave us a small epsilon, I'm going to make delta equal to something else. But by ignoring all the big epsilons, we can say something about the smaller epsilons. And what we can say is basically, we know that the absolute value of x minus 2 is always smaller than delta. But if we're saying that delta is at most 1, then the absolute value of x minus 2 is smaller than 1. So then negative 1 is less than x minus 2 is less than positive 1. So then 3 is less than x plus 2 is less than 5. So then this, x plus 2 times delta, is smaller than 5 times delta, because I know that absolute value of x plus 2 has to be smaller than 5. Does that make sense? Yeah. It's a bit weird to think about like why we're ignoring it, all the big ones. But it's basically we just don't want to have to focus on them when we can pick an easy delta that'll work for all of them. We still have to look at the little ones. So now I'm saying, using this inequality, the absolute value of x squared minus 4 is smaller than 5 delta, and it's also smaller than epsilon. So then I can let my epsilon equal 5 delta in the case where x minus 2 is smaller than 1. Or in other words, my delta would be the minimum. Sorry, if I divide both sides of this, my handwriting is getting worse and worse. If I divide both sides of this by 5, I would get delta as epsilon over 5. So my delta I would pick to be the minimum of 1 and epsilon over 5. Does this whole process make sense? When do we use the equation with the a plus r? With the a plus r, so this might be the like a plus r equation your professor might have been talking about. In this case, I'm not quite sure though. I'm maybe not quite sure with what your professors. They would have added 2 to 1. Okay, so that is definitely doable. So like they would have added, they would have turned this into 1 is less than x is less than 3. Something like that. Yeah. So this is another valid way of doing it. They might just be showing you because x minus 2 is less than 1, then you can get to this. And from this, then you can say that 3 is less than x plus 2 is less than 5. Because you're trying to say something about this x plus 2 right here. You're trying to substitute it out for an actual number. They might just be turning it into an intermediate step. Yeah, it's just the same thing with x by itself. But any other questions? All right. In that case, I'm going to stop recording.